This is lesson 8.2.1, Confidence Intervals for the Difference in Two Population Proportions. Introduction. In lesson 8.1.1, we examined media habits of the millennial and baby boomer generations. In particular, we compared these two generations according to the proportions of adults who used Facebook as a source for political news. We noticed possible differences between the two proportions. In this lesson, we will explore how differences in sample proportions can be used to estimate the difference in population proportions. Using specific differences in sample proportions of millennials and baby boomers who used Facebook for political news, we will construct confidence intervals for the unknown difference in the population proportions. In the two dot plots below, each dot represents a random sample of adults from either the millennial or baby boomer generation. The location of the dot on the x-axis shows the proportion of millennials or baby boomers in that particular sample who relied on Facebook for political news. As in the simulation examples of lesson 8.1.1, 100 different samples of size 65 from the millennial population were randomly generated. Similarly, 100 different samples of size 50 were generated from the baby boomer population. Okay, so again, these are 100 different samples of different sample sizes for the baby boomers and the millennials. Okay, and this is the proportion of them that relied on Facebook for political news. Throughout the discussion, approximate normality of the sampling distributions is assumed. This means we assume that the underlying sampling distributions are roughly normal. Recall, this assumption requires that n times p and n times 1 minus p are both at least 10 for both the populations of millennials and baby boomers. We will first revisit how a distribution of differences in sample proportions relates to the individual distributions of sample proportions. Compare these distributions of sample proportions in terms of center, shape, and spread. So center, pick a value that best represents each distribution from the dot plots above, one for the proportion of millennials and one for the proportion of baby boomers. Okay, well, let's see. If I look at the millennials, I would say that probably .6 best represents. That looks like the middle to me. For baby boomers, I would also say, so it looks to me like something like this is the middle. So that's a little bit above the halfway, so that's like 0.36 maybe. So this is just me roughly eyeballing here. Okay, so for millennials was the top one. So millennials was 0.6, and then we have 0.36. Now let's go to shape. Examine the shapes of the distributions. Do these distributions of values appear as if they may be drawn from a normal population? Well, these both look pretty normal to me. Something like that, and something like that. I mean, it looks roughly normal, right? So I would say yes, both look roughly normal. And now let's compare their spread. It says let's look at both distributions and compare their spread. So what do we think? Does this look about the same? I would say that the millennials look a little more spread out, just because I would say that maybe most stuff lies here. But for millennials, we actually have quite a bit at the edges, so I would say that most stuff lies here. So I do think the millennials are more spread out. So let's just say millennials seem to have a higher spread. Okay, let's keep going. The dot plot below displays the distribution of all differences in proportions between millennials and baby boomers. So what this means is that we're looking, well, actually, let's keep reading here. This dot plot combines the information from the two dot plots above. Each dot represents the value PM hat minus PB hat from two independent random samples. The value PM hat minus PB hat is the difference between proportions of millennials and baby boomers. Notice that the proportion of baby boomers is subtracted from the proportion of millennials. Okay. So again, every dot here corresponds to, if you were to take two dots randomly from each of these and then subtract them, that would give you a dot over here. And it's in the order millennial minus baby boomer. So first it says, estimate the mean of the distribution of differences, PM hat minus PB hat. So we're choosing something that represents what we think the mean is here. I'm going to say the mean is probably right around here, right? Which is about 0.23. So let me go ahead and write that down. The mean could even be 0.24 because it looks like it's almost at the midway point. The mean is about 0.20. Yeah, I'll go with that. 0.24. Right, it's a little hard to tell. How does the mean of the distribution of differences compare to the representative values from the individual distributions of proportions in question 1a? Well, if we look at question 1a, we have these two values here, and I want us to think, how does 0.24, the number we just got, relate to these two means? Well, 0.6 minus 0.36 is equal to 0.24. Okay, so what that means is the difference in the means equals the mean of the differences. Okay? Difference in means equals mean of differences. That's sort of the big idea here. In lesson 8.1.1, the population proportion were assumed to be PM equals 0.61 and PB equals 0.37. How does the mean of the distribution of differences relate to those population proportions? Again, PM minus PB is 0.61 minus 0.37, which is 0.24. So there you go. Next steps. The previous set of questions highlighted the following key statistical principle. The mean of all differences is the difference of the means. Symbolically, this can be expressed as the mean of the difference distribution is equal to the difference in the two individual means. So if we were to look at a picture to help us with this, it means that the mean of this picture minus the mean of this picture gives us the mean of this picture. Okay. Let's examine how we can estimate the difference in population proportions when these proportions are unknown. To estimate the difference in population proportions, we find a difference in sample proportions and use it as a point estimate for the unknown difference in population proportions. In addition to the point estimate, we must find the estimated standard error of differences in sample proportions. So in essence, guys, what we're working towards in this lesson is how to build a confidence interval for the mean of a difference distribution when you do not know the real answer, okay? So this is just like our previous work with confidence intervals. The only difference now is that we have two proportions instead of just one. So the estimated standard error of differences in sample proportions is based on the sample proportions PM hat and PB hat, and it's found using this formula. Okay, so this is going to be our formula. This should seem familiar, right? This is just like the formula we used in the previous two sections. The only difference, though, is that we don't have just P, the P has hats in this one instead of not having hats in the previous lesson, right? The reason for that is we do not know the real answer, so of course all we have is our sample proportions to go off of. And this should remind you of what we did before when we were doing confidence intervals at the beginning. Margin of error. Recall that the margin of error, E, for any normally distributed unbiased estimate of a population parameter is E is equal to the critical Z value times the standard error. In this formula, ZC is the standard normal critical value. It corresponds to a level of confidence. The table below, which you have seen in previous lessons, summarizes the most common confidence levels and their associated standard normal critical values, ZC. Okay. So language tip here, it says words like correspond, associated, and respective help us keep track of relationships between values and confidence levels or other statistics. So if we look here, confidence level, critical value, this table should look familiar. We use this exact same table when we were doing confidence intervals in Module 7. The only difference is now we're going to be using the confidence intervals to tell us the difference in sample proportions, okay? So these are the values. And look at this formula. The E is going to equal the Z value times the standard error. Remember, the standard error is given by this, okay? So this becomes our formula then. Using the estimated standard error formula above, the margin of error becomes right there, okay? It's that formula. It should look familiar to you. The only difference is that there's more stuff under the square root. Confidence interval for the difference in population proportions. Recall that confidence intervals have the general form statistic plus or minus E, or using interval notation, statistic minus E, statistic plus E. In the context of the difference in two population proportions, the statistic is the difference in sample proportions. So the confidence interval is PM hat minus PB hat minus E, and PM hat minus PB hat plus E. Okay, so this should look familiar to you, right? Because in Module 7, we did this. Right? This was in Module 7, when you have one sample proportion. However, now what we're doing is we have two of them, and so we're replacing p hat with pm hat minus pb hat. And so that's why the p hat got replaced with those. Okay? Let's keep going. In question 1, you identified representative sample proportions from the individual sampling distributions of sample proportions. Let's use these values to construct a 95% confidence interval for the difference in population proportions PM minus PB. Use the values for PM hat and PB hat from question 1 and the sample sizes NM equals 65 for millennials and NB equals 50 for baby boomers to calculate the estimated standard error of differences. Okay, so we're going to plug in all the numbers that we get from question 1. First, we need to look at what PM hat is. So let's go back. Oh, it says in question 1. So let's go over to question 1. So we're using the 0.6 and the 0.36, right? We're not assuming that we actually drew samples here. Remember, we picked a value that we picked these values ourselves, so these are ideal, right? So 0.6 and 0.36. So it's 0.6 times 1 minus 0.6 divided by 65 for millennials plus 0.36. Let me make sure it was 36. I think so. Yes, 36. 0.36 times 1 minus 0.36 divided by 50. So we get that. What does this equal? We're going to use our calculator for this, and I'm going to cut to it because this is a slightly complicated one. So let's see what we get. So let's see what we get for the estimated standard error. I'm using my calculator here. I'm going to do the second square root. And remember to put parentheses around the whole thing because we're going to have, well, actually, in my calculator you don't need to, but in some you may if the square root sign doesn't keep extending. So I'm going to do 0.6 times 1 minus 0.6, close parentheses, divided by 65, plus 0.36 times 1 minus 0.36, close parentheses, divided by 50. So if we do all that, we end up with 0.091 if we round it to 3 decimal places. Okay, so we get 0.091. All right, so remember what we did in the past. Okay, we took that standard error and we multiplied it by the critical z-score that we care about. So in part B, it says compute the margin of error for a 95% confidence interval using the estimated standard error computed in question 3A and the appropriate value of ZC from the table above. Okay, so let's go ahead. We want a 95% confidence interval, so we're going to use the critical z-score of 1.96. You don't need to put the last 0 there just because it's irrelevant, right? Doesn't change anything. So 1.96, and we're going to multiply it by 0.091. What does this give you? We get 0.178. 0.178. All right, so this would be our margin of error. So let's move on. It says compute the 95% confidence interval for the difference in population proportions PM minus PB. Write your answer in interval notation. Okay, so what is PM hat minus PB hat minus E? And then we also have to calculate PM hat minus PB hat plus E. So remember, if we subtracted those guys, we got 0.24. So it's 0.24 minus 0.178, and then 0.24 plus 0.178. Let me go ahead and do that in the calculator. So if I subtract 0.178, I end up with 0.062. And then if I add 0.178 to it, I end up with 0.418. Let's look at part D. Oh, sorry, before we do that, so what would the confidence interval be? It goes from 0.062 until 0.418. So this is the confidence interval. Remember, we always need to write our confidence intervals like that, with parentheses, lower limit, comma, upper limit. Okay, so does your confidence interval allow for the proportion of millennials and baby boomers who used Facebook to be equal? So this is a common question that you're going to see in these difference problems. Your confidence interval only allows for the proportion of millennials and baby boomers to be equal if 0 is contained in the confidence interval. So question, is 0 contained in this confidence interval? Think about going from 0.062 to 0.418. This thing does not contain 0. How do you know that? Well, 0 is to the left of that, right? But an easy way to know if 0 is contained in an interval of numbers, the only way that an interval can contain 0 is if it goes from negative to positive. And this is positive the entire time. So, no, our confidence interval does not allow for the proportion difference to be 0, since it is positive. Let me be a little more specific. Since the confidence interval is positive the whole time. Sorry, just to clarify here, this is part of something different, okay? Finally, we can interpret this confidence interval in the context of this situation, okay? The most important part, of course, is explaining this, right? Being able to explain what we just found. So we would say, always start by stating how confident we are. We are 95% confident that the difference in the proportion of millennials that use Facebook for political news and baby boomers who do the same is between 0.062 and 0.418. Okay, so remember, we are not finding a single proportion here, but we're finding the difference. And so what we're saying is that if you take one and subtract the other, that it's going to be somewhere between those two numbers, and that we're 95% confident of that. Okay, let's keep going. Each difference in sample proportions will lead to a different interval estimate. Sometimes there are extreme cases of confidence intervals that do not contain the difference in population proportions. To create an extreme case of a confidence interval, pick extreme values for PM hat and PB hat and create the corresponding 99% confidence interval. Okay, so we are going to do something a little weird, right? Because we chose values that were close to the middle before, but what if I now choose values that are really off just to show you what will happen, okay? So we're going to, this first question asks us to, from the dot plot of proportions of millennials who used Facebook, pick the largest of the simulated sample proportions. The largest. So that would be one of those, right? What's that? That's slightly below 0.75, so I'm going to go with 0.74. Let me go back here. 0.74. Okay. All right. So that's what I get for that guy. And then the next one says, from the dot plot of proportions of baby boomers who used Facebook, pick the smallest of the simulated sample proportions. The smallest. Okay, so they're asking us to do this, so we're going to do it, okay? We're going to go with the smallest. Where would that be in the picture? I'm going to go with 0.23 for that one, okay? 0.23. So let me write that down. What is the difference in these sample proportions? So I'm going to subtract the two numbers I just got. So 0.74 minus 0.23. What do we get here? We get 0.51. So we're going through and we're purposely creating a confidence interval using extreme values to show that you could be misled if you get unlucky. Of course, this is pretty unlucky to get the absolute furthest values from the middle, right? When you do a sample. But again, this can happen a small percentage of the time. Okay, so let's see what happens here. We're going to put this into our calculator. We have in the square root, we're going to have first foot for the millennials. Remember, the millennials were 0.74. So we have 0.74 times 1 minus 0.74 divided by 65 plus, and then we have 0.23 times 1 minus 0.23 divided by 50. Okay, so let's see what we get on our calculator, which I will show again. So let's see what we get here. So I'm going to go over to my calculator. This is going to be second square root, and then I have 0.74 times 1 minus 0.74 divided by 65 plus 0.23 times 1 minus 0.23 divided by 50. Put all that in, hit enter, and we get 0.081 if we round it up. So this is equal to 0.081. Okay, so we're ready for the standard error. This is going to be, if you recall, so 99% confidence interval, we're going to check out the confidence level here. For 99%, we use 2.576, okay? 2.576. 2.576 times the standard error. So I'm just going to multiply this by 0.081. So if I multiply this by my calculator, I get 0.208. So this would be the margin of error. So now we're going to compute the 99% confidence interval for the difference in the population proportions PM minus PB. So remember, first we do PM hat minus PB hat minus E, and then we do PM hat minus PB hat plus E. Okay? So what would that give us? If you subtract these two, remember we got 0.51, so it's 0.51 minus 0.208. And then 0.51 plus 0.208. So let's see what we get here. If you do 0.51 minus 0.208, we get 0.302. If you do 0.51 plus 0.208, we get 0.718. So this means that the 99% confidence interval, so 99% confidence interval is 0.302 and then 0.718. Notice how different our answer was when we used the extreme values, okay? All right, so let's keep going. It says, look back at question 2A. Assume that the estimated mean of the differences in question 2A is the actual mean of the differences. That is the true difference in population proportions, PM minus PB. What is the value of the difference in population proportions? So let's look back at 2A. So remember, we got 0.24, right? 0.24. Is this difference in population proportions contained in the confidence interval from question 4F? Well, 0.24 is not in there, is it? Right? Because we're going from 0.302 until 0.718. So no. 0.24 is not in the confidence interval. We found that the most extreme value of PM hat minus PB hat generated a confidence interval that does not contain the difference in population proportions. The result here is not typical of what generally happens when sample proportions are gathered randomly. What proportion, so let me back up for a second, okay? Do not be worried that we made a confidence interval that did not contain the real answer. Right? Because we purposely chose values that were really far away from each other, right? This is not generally going to happen when you choose random samples. The whole point is that you're going to typically, most of the time, get close to the mean, right? Look at all those dots. Okay, so we purposely created a bad value here, okay? What proportion of 99% confidence intervals can you expect to not contain the true difference, as has occurred here? Well, think about it. If we're 99% confident that this contains the answer, then that means only 1% of the time will it not contain the true difference. Okay, so 1% of all 99% confidence intervals will not contain the true difference in population proportions. Okay, so you need to know, we now summarize the steps to construct a confidence interval for the difference between two population proportions. By the way, guys, the code word for this lesson is millennial. Okay, please remember that. Code word for this lesson is millennial. So let's keep going here. Summary. Confidence intervals for a difference between two population proportions. This summarizes everything that we just learned in this section. So step 1, you verify the approximate normality criteria. Remember, the approximate normality criteria are that n times p hat is greater than or equal to 10, and n times 1 minus p hat is greater than or equal to 10. You need to do this for both P1 and P2, for both of them. Also, it's important here, notice that in confidence intervals, you don't use the real P because you don't know it. That's the whole point of doing this, right? So we use P hat when we don't have P. Remember that each sample should have at least 10 successes and 10 failures. That's really another way of saying this sentence, okay? Step 2, in the table of critical values, find the critical Z value, ZC, corresponding to the chosen confidence level. Step 3, compute the margin of error, and you get that from doing this formula, right? You can do ZC times that big square root. And yes, you can do it all at once. You do not have to do the square root first and then multiply it by ZC, but you can do it all in one step. Step 4, construct the confidence interval. Remember, the confidence interval is always the difference minus E and then the difference plus E. Interpret the confidence interval in the context of the problem. Again, this is the most important step. Make sure the meanings of the population proportions are clear from your description, right? Don't just say P whatever. You want to say the proportion of millennials who believe in whatever, right? You want to make sure you say specifically what you're talking about. And use your chosen confidence level to describe how confident you are that the interval contains the difference in population proportions. Okay, everybody? That's it for this lesson. Thank you very much for watching. Hope the video was helpful.